Here are the conclusions that we can draw from these results. If we look at the cases for A and B, if we remember from the table that we saw with the actual experiments, in these cases, we had a fairly nice mix of tasks with different CPI values on each of the cores. So in these cases, the processor pipeline was well utilized and we're obtaining a high IPC. It is not the maximum IPC of 4, so the maximum performance that one can obtain on the processor that Fedorova is simulating, but it's fairly high. If we look at the cases for C and D, in these experiments, each of the cores was assigned tasks that had much more similar CPI values. In fact, in the case of D, every single one of the cores ran tasks that had the exact same CPI value. So if we take a look at these results, we see that the total IPC is much lower than what we saw for the case A and B. The reason for that is that on some cores, like on core 0 in particular, but also on core 1, there is a lot of contention for the CPU pipeline. So these are the cores that mostly had tasks with a low CPI. So mostly the compute-intensive tasks were here. On the other hand, cores 2 and 3, they contribute very little to the aggregate IPC metric. So basically, they really execute only very few instructions per cycle, or a few small percentage of an instruction per cycle, rather, given that a maximum is 1. The reason for that is that we mostly have memory-intensive tasks on these two cores, and that leads to wasted cycles on them. So by running this experiment, Fedorova confirmed her hypothesis that running tasks that have mixed CPI value is a good thing, that will lead to an overall high performance of the system. So the conclusion from these results is that CPI is a great metric, and therefore we should go ahead and build hardware that has a CPI hardware counter and tracks this value, so that we can then go ahead and also build operating system schedulers that use this value in order to schedule the right workload mix. Not so fast. In our discussion so far, in the experimental analysis, we used workloads that had CPI values of 1, 6, 11, and 16. And the results showed that if we have such a hypothetical workload that has such distinct and widely spread out CPI values, the scheduler can be effective. But the question is, do realistic workloads have CPI values that exhibit anything that we used in the synthetic workload? To answer this, Fedorova profiled a number of applications from several benchmark suites. And these benchmark suites are widely recognized in industry and in academia as well, that they include workloads that are representative of real-world relevant applications. And let's look at the CPI values for all of these benchmarks. We see that they're all sort of cluttered together. There aren't such distinct CPI values like 1, 6, 11, and 16 as what she used in her experimental analysis. What this tells us is that although in theory it seems like a great idea to use cycles per instruction as a scheduling metric for hyper-threaded platforms, in practice, real workloads don't have behavior that exhibits significant differences in their CPI value, and therefore CPI really won't be a useful metric. So I showed you a paper about something that doesn't work. There's still some very important takeaways from this paper. First, you learned about SMTs and some of the resource contention issues there, specifically regarding the processor pipeline as a resource. Next, you learned how to think about the use of hardware counters to establish some kind of characteristics about the workload, to understand it better so that you can better inform the operating system level resource management. In addition, you learned that it is important to design schedulers that will also think about resource contention, not just about load balancing. For instance, a scheduler should think about choosing a set of tasks that are not going to cause a resource contention with respect to the processor pipeline or the hardware cache or the memory controller or some type of I/O device. So these principles generalize to other types of resources, not just to the processor pipeline in hardware multi-threaded platforms. And by the way, in Fedorova's follow-on work, as well as several other efforts, It's been established that a particularly important contributor to performance degradation when you're running multiple tasks on a single hardware multi-threaded or multi-core platform is the use of the cache resource, in particular the last level cache. So what that has told us is to, for instance, keep track of how a set of threads is using the cache as a resource and pick a mix that doesn't cause contention on the last level cache usage. And this is just for your information. We're not going to look in any additional papers that really further explore this issue, not in this course at least.